Okay, in this video, we're going to look at a fundamental phenomenon of carbohydrate molecules. And this arises from the equilibrium between carbonyl forms and hemiacetal forms. Okay, you may recall this from back in the ketone aldehyde chapter, that when we react to ketone with an alcohol, we reversibly form a hemiacetal. Okay? All right. So in most cases, this equilibrium arrow goes heavily to the left. Okay? All right, but there's an exception to that, and that's when your acetal or hemiacetal formation is intramolecular and making either a 5 or a 6-membered ring. If this is the case, then the hemiacetal form becomes the major species at equilibrium. Okay, so we're going to take this alcohol right here that has an OH group on the 4th carbon down the chain, and it makes a 5-membered ring hemiacetal. Okay, and this one, which has a 1 carbon longer chain, makes a 6-membered ring hemiacetal, and the equilibrium favors the hemiacetal form. Okay, this new carbon, or this new stereocenter that we have here, this sp3 carbon that I've indicated with an asterisk, is going to have a special name. It's going to be called the anomeric carbon. It's the carbon that in the open chain form was a C double bond O. And this is how you recognize the anomeric form. It's the only carbon that has 2 oxygens on it. Okay, so if you look at this asterisk carbon, there's 1 oxygen and 2 oxygens attached to that carbon, and that's what defines the anomeric carbon. Okay, what's the reason for this exception here? It has to do with the fact that equilibrium is governed by delta G and not delta H. Okay, so when you look at how delta G relates to delta H, there's this other component, entropy, here, and what is happening here in this very top equation is that 2 molecules have to get together and make 1 molecule, and that's entropically disfavored. Okay, but in this case, it's more or less entropically neutral because we don't have the number of molecules involved is the same, and we don't have to adopt an unstable ring system. The ring system is actually very favorable. So for this combination of ring size features and entropy features means that forming the cyclic hemiacetal to make a 5 or a 6-membered ring is inherently going to be more favorable from a delta G standpoint because of the entropy component being much, or not being detrimental as it is in the top. Okay, so 2 molecules become 1. That's bad entropically. 1 molecule becomes 1. This is kind of entropically neutral. Okay, so it's delta G is a little bit more negative. Okay, all right. So let's answer this question here. Which compound is going to have the highest percentage of hemiacetal form at equilibrium? What are our considerations here? Okay, the hemiacetal is only going to be stable if it makes a 5 or a 6-membered ring, so we can eliminate this last one. Okay, so in this last case here, if this oxygen attacked like so, we would get a compound that has a 4-membered ring, and this is not going to be very favorable. Remember, 4-membered rings also have a lot of angle strain. Okay, all right, so what's our other governing factor here? It's the fact that electron withdrawing groups destabilize ketones. Remember, ketones have a partial, or aldehydes have a partial positive charge, and an electron donating group is going to stabilize that, make it less reactive, make it more stable, but an electron withdrawing group is going to destabilize it. So if you destabilize the carbonyl form, it means that you're going to see more hemiacetal at equilibrium. Okay? All right, so the electron withdrawing group destabilizes the carbonyl group form, so that is the one that's going to be more likely to make a hemiacetal. Okay, so let's just go ahead and draw that hemiacetal. Okay, so there we go. Okay, now what does this have to do with carbohydrate chemistry? Of course, you probably see an obvious relationship. Carbohydrates have OH groups and C double bond O, so they're going to, of course, be subject to this. All right, so let's look at the simplest molecule that can make a 5-membered ring hemiacetal, and that would be an aldotetrose. Okay, so we'll just use D-erythrose as an example here. All right, we're going to make a hemiacetal between that oxygen and the carbonyl group. Recognize that this is going to be, and that oxygen makes the 5th member of the ring, so this is going to be a 5-membered ring hemiacetal. And recognize that our anomeric carbon in this case actually is a new stereocenter, right? Because it's sp3 and it has 4 different things on it. Okay, it was not a stereocenter here where it's sp2, but when it's sp3, it's a chiral center. Okay, and so when you close the ring here, there are 2 possible compounds you can get. The one where the OH is down on the left and the one where the OH is up on the right. Okay? All right. So this drawing here has a special name. This is called the Haworth projection. And in a 5-membered ring sugar, they're always drawn like this, where the oxygen is to the back and the carbons of the 5-membered ring are coming out at you. Okay? All right, so as long as everybody draws their compounds from the standard recommended orientation, it's very easy to see how the Haworth projection relates to the Fisher projection that you started with. Okay? All right. In general, an OH that goes to the right in the Fisher projection is going to go down in the Haworth projection. Okay? And an OH group going to the left is going to go up. The situation is more complex if the OH is used to make the hemiacetal. Okay, so in this case we don't have to worry about it because this OH right here is on a carbon that's not a chiral center. So that's we're going to take care of that complication in the next one here. So it's not a chiral center. Okay, so this one's relatively easy. Okay, so this is the take-home lesson here, that when an OH going to the right is down, an OH going to the left is going to be up. Okay? All right. The alpha anomer has the OH at the highest number chiral center, in this case, right there. And the OH at the anomeric carbon in the same orientation. Okay? If drawn from this perspective, though, we can just remember that OH down at the anomeric carbon is the alpha anomer, okay, and OH beta is the one where this is up, okay. So these 2 compounds here, all right, we're going to refer to them as being anomers. They are diastereomers that differ only at the anomeric carbon. I'm going to draw a Venn diagram here. So here's all the diastereomers in the world. Okay, many diastereomers are epimers, and a subset of that would be anomers. Okay. All right, so all epimers are diastereomers, all anomers are epimers, and ergo also diastereomers. Okay, all right, so an anomer is a diastereomer or epimer that differs only at the anomeric carbon. And when you consider the open chain form, the two anomers actually go back to the same open chain form compound. These are both D-erythrose, but D-erythrose, the aldehyde carbon is sp2, so it's not a stereocenter. It doesn't become a stereocenter until it becomes the cyclic form or the hemiacetal form. Okay, so D-erythrose, the chain is not long enough to make anything but a 5-membered ring hemiacetal. Okay, what about D-ribose? D-ribose is a little more interesting because we have the possibility of making either 6-membered rings or 5-membered rings. In fact, when D-ribose is completely at equilibrium, all right, we find that very little of it is in the open chain form. Almost all of it is in one of these 4 closed orientations, okay? All right, so what we see here is that most of it is in a 6-membered ring, okay? All right, so the 6-to-5 ratio, we'll say, is 76 to 24, okay? Add these two numbers and compare them with these two numbers. So there's more 6-membered ring than 5-membered ring. This is a general trend that you should remember from a very early part of the first half of this class, that 6-membered rings are the lowest energy ring systems of them all when you're looking at rings that only have sp3 carbons. Okay, 5-membered rings are a little bit higher in energy. Now, I have to tell you that if you go on to a graduate class here, we're going to learn that carbohydrates are a little special. There's a lot more things that are contributing to the energetics of these species. But for one of the important ones is this ring size consideration right here. Okay, all right, so we have more 6-membered ring than 5-membered ring. When we have a 6-membered ring sugar, we're going to give it a special name. We're going to call it a pyranose. And when it's a 5-membered ring sugar, we're going to call it a furanose. And what we're going to do here to the name is refer to the stereochemistry of the anomeric carbon right there. And right here, this is going to indicate whether we're dealing with a 5 or a 6-membered ring. Okay? All right. So again, alpha ribofuranose, beta ribofuranose. Okay? All right, if the OH that's used for the acetal formation is to the right, then the CH2 group is going to be up when we use this perspective. And this is the standard Hayworth projections for 5- and 6-membered rings. For 5-membered rings, it's just like we saw in the previous one. But in the 6-membered ring, we say we have the oxygen over to the northeast. Okay? And the chain coming out at us. Okay? All right. Let's look at the ribopyranose form in a little more detail here. Okay? In addition to the Hayworth form, when it's a 6-membered ring, there's another form that's, or another way that we draw this that's also very important, and this is called the chair form. This is just good old chair cyclohexane from a very early part of the first half of the class. Okay, when we draw the ribopyranose form, the alpha ribopyranose form here, we get the axial OH group, and when we draw the beta ribopyranose form, we get the equatorial OH. Okay, so we probably remember long time ago in this class, we remember that larger groups want to go equatorial, and that could be a reason here, but I'm going to just tell you that there's other factors at work here, but this is a good first approximation, maybe, that we're seeing more of the form where the OH group is equatorial. Okay, there is some factors that are stabilizing the axial, but steric, if we consider only sterics, the equatorial OH should be favored. Okay, D-glucose exists primarily in the six-membered ring form. Okay, and here is glucopyranose as a Hayworth projection right here. Here's our Hayworth. Now let's put the Hayworth into the chair form. And what you'll notice here is that glucose is a very special molecule. And when you have the OHs in this orientation and you now draw the chair, everything is equatorial. In this case, the OH, that's the anomeric OH, is still axial or equatorial. Okay, these two compounds are anomers, the alpha anomer and the beta anomer. The beta, everything's equatorial, and the alpha, everything except the anomeric carbon is equatorial. Okay, so it's probably for this reason that nature chose glucose as the primary molecule to transmit energy in living systems. Okay, it's the most stable form that we can have. It's the only one where you can have all of the OH groups equatorial, again, except for the anomeric carbon, which has the choice to be axial or equatorial. Okay, we see a little bit more of the one where there's more of the equatorial form, the beta anomer, there's more of it. Okay, all right, so let's just end this video with one exercise. We're going to place asterisks beside the three anomeric carbons in this molecule here, which is a trisaccharide. And what are we looking for in when we're looking for the anomeric carbon? We're looking to find one unique sp3 carbon that has two oxygens, okay? All right, so if you look at this molecule, there's one right there, okay? There's one right there. That carbon has two oxygens. And this carbon right here also has two oxygens on it. So those are our anomeric carbons. If we hydrolyze this and turn each of the three saccharide units into a Fisher projection, we'd find that those asterisk carbons were the ones that would correspond to C double bond O's in the open chain forms. Okay, so we're going to stop this video and then we're going to look at reactions of carbohydrates in the next one. Okay.